in the support class plot, which usually go over it this time. So finishing up chapter 8, A586. Pearson quiz goes live at 1:15, due tomorrow night, Friday night, 11:59. 2 attempts possible, keep the best score. Don't forget to try the quiz practice. Need some guidance with the quiz practice, watch the support class today YouTube video. So the 827 support class YouTube video, we walk through everything. I'm going to hand out here, I have the summary and practice test, or summary and practice problems for chapter 8. I'll hand that out to you, but it's also going to post on the announcements on Canvas. It's also going to be an attachment with your video link. On Tuesday next week, we review for chapter 9, and I'll review for chapter 8, preview chapter 9. Thursday is chapter 8 test. You do get to use a note card, 3 inches by 5 inches. Note card must be handwritten. With a reminder, last day to drop a class is Friday. Tomorrow, Friday. Add or drop a class. No. So let's just run through. Hopefully there's a pretty well obvious as to what's the least common multiple for 4 and 7? Mm-hmm. 28. And least common multiple for a 3 and 10. 30. And least common multiple for a 5 and a 20. So 5 and 12. What is it? 60. And least common multiple for 8 and 9. 72. And if you are teaching, again, focus on your future career, each young student. What wrong impression did this give? Yeah, you just multiply those numbers. It's a multiple, yes. Could it be the least common multiple? Sometimes, yeah. But if we're looking for the least common multiple between a 4 and an 8, 32 is not the least common multiple. It is a multiple. If you want to make your denominators, you have 3/4 plus 5 over 8, and you want to just get the common multiple and make the denominator a 32 and a 32, be my guess. A common multiple is perfectly fine. Multiply the 4 and the 8. Multiply this one by 8 over 8. So this is now 24 over 32. That'll multiply this by 3 over 3. So 38. 4 over 4. So this is now 20 over 32. So when I add those two fractions together, 24 plus 20, that's 44 over 32. And you start to walk away, and it's wrong because it's not reducing those terms. So now you need the greatest common factor that goes into both, or maybe you just whittle it down. They're both even. So we go, all right, that's 2 times 22, and that's 2 times 16. So that reduces. So then you're okay, my final answer, 22 over 16. Well, that's not right, because it's still not in those terms. They're both even still. So we have to keep on going. So that's now 2 times 11 over 2 times 8. So you can reduce 2 one more time. So your final answer should have been 11 over 8. But, and I know a lot of students will say, can't we just multiply the 2 numbers together and get it the common denominator? It's not the least common, not always. a 4 and an 8. What's the least common denominator? So let's say, what is the least common multiple? What's the smallest number that both go into even? 4 goes into 4, 4 goes into 1, 8 goes into 8, 8 goes into 16. What would be the least common denominator? What? Or 4 to the 8. Least common multiple. You're going to add those fractions. So I don't have to do all that extra work. 4 and 8 both go into. Is that? That's what it did use. Look at all the extra work it had. That's what the student is thinking. I'll just multiply this together and I'll always get the, it's not going to be the least common multiple. That's not how you find them. It worked out for these because they had no other factors in common. See? 16 is a smaller one. Is there anything smaller than 16? 8. The first number, if you list out the factors of a 4 and an 8, 4 goes into 4. 1 times 4, 2 times 4 is 8, 3 times 4 is 12, 4 times 4 is 16, 8 times 1 is 8. They go from 1 to 8. That's the smallest number that each one goes into. If you did the slide method, if we did the slide for a 4 and an 8, what's the biggest factor? What's any factor you can take out of a 4 and an 8? What do you want to take out? Take out 2. So I take out a 2, 4 divided by 2. I think I can get this one right. I get a 2. 8 divided by 2, I get a 4. Is there anything left that you can take out? What's that? Another 2. So I factor out another 2. I get 2 divided by 2. That's a 1. I get 4 divided by 2. That's a 2. So my least common multiple is 2 times 2. And then turn that, make that right hand turn there. 1 times 2. 2 times 2 is 4, times 1 is 4. 4 times 2 is 8. If you use the slide method. If you list the factors, first number they have in common, list the multiples, chart says that. If you list the multiples, the first number they have in common for both. 8. Don't forget about that. But does 32 work? Yeah. But you got to remember to reduce the lowest terms. That's more said. Look what happens if I just use 8. So I want 8 down here and 8 down there. To change this 4 and make it an 8, we got to multiply by 2 over 2. 2 times 4 makes by 8. The numerator is now 2 times 3. That's a 6. That's already an 8. So we don't have to change this one at all. It stays 5 over 8. So now 6 over 8 plus 5 over 8 is 11 over 8. The smaller the common factor, the smaller the common multiple, the smaller the common denominator, the least common denominator, less work to do will be done. That's the key. But we have to be able to separate the words least common multiple, least common denominator from greatest common factor. What do they go into versus what goes into them? Okay. And it takes practice. Okay. When you come across a problem of three, you cannot use the slide method on three at a time. You can only use the slide method for two. And that really goes for anything you want to do. You can only do two at a time. If you wanted to multiply, let's go with 4 times 5 times 6. Nobody on the face of the earth can multiply those three numbers together all at once. Nobody knows or can multiply those numbers all at once. No matter what, somebody's going to go, all right, 4 times 5, 20, and then times 6, 120. Or they're going to go, this is 4, 5 times 6 is 30, 4 times 30, that's 120. Or they might even go, 4 times 6 is 5 times 24, 5 times 24, that's 120. But they're going to multiply two numbers and then multiply the third one. If I was looking for the least common multiple using the list method for a 4, a 5, and a 6, then what I would do is I would pick two numbers, any two numbers, and start there. If I'm going to find the least common multiple for those three, I have to make sure it goes into two of them. So which ones do you want me to start with? The 4 and the 5, the 5 and the 6, or the 4 and the 6? 4 and 6. So if I start with 4 and 6, so 4 times 1, 4 times 2, 4 times 3, 4 times 4, 6 times 1, 6 times 2. So the least common multiple for the 4 and the 6 is a 12. And so the 4 and the 6, now I have to find the least common multiple for that 12 and the 5. Because I already know that 4 and 6 are going to divide into 12. So if I can find the least common multiple for that 12 and the last one 5, then 4, 6, and 5 go into. So I can go 12, 24. If it's going to be a 5, it has to end in a 5 or a 0. 24, 48. Oh, there's 6. You know what? I missed one. 36, 48, and then 6. So the first number that 5 is going to be able to divide into, 5, 10, is going to be 6. That's the only one that ends in a 0. So the least common multiple for these three numbers is 60. Could I multiply all three together? Absolutely, but it might not be the smallest one. If I multiply all three of these together, 20 times 6 is 120. That's bigger than that one is. I'm going to have more work to do. So when we use the slide method, you find two of them, least common multiple, take two, find it, and then you use that answer with the third one. But here's the example. This is going to be a test question. The biggest mistake I always see is they try to use the slide method on all three at the same time. So the slide method, which two do you want to try to accomplish? 45. So 45 and 40. 45, 40. What's the bigger factor for 45 and 40?
5.
So we get 5. 45 divided by 5 leaves you 9. 40 divided by 5 leaves you 8. Anything left? Any factors left out of a 9 and an 8? Nope. So the least common multiple for the 45 and the 40 is going to be equal to 5 times 9 times 8. For me, it looks like I'd rather multiply the 9 and 8 first. So that's 5 times 72. Because 5 times 70 is 350. And then 5 times 2 is an extra 10. So 5 times 72 is 360. And you're right. I'm also going to have to check. So now the answer for this right here is 360. Now we got to find the least common multiple of this 360 and the 125. So we go one more time. 360 and the 125. Pick a number. Goes in each one. 5. So 360 divided by 5, and that's going to go in 72 times. That's right there. And this is 5 times 25. Well, 125 divided by 5 is going to be 25. So now you're left with 72 and 25. 72 and 25. Anything in common? Nope. So the least common multiple between this answer, which involves 45 and 40, and the 125 is 5 times 72 times 25. So 5 times 72, well, that's 360 times 25. 300 times 25 is 75, and a couple of zeros, and then 6 times 25 is 150. So 150 with an extra zero. And 300. 1. So I have 9,000. All right?
Yes.
Okay. So the least common multiple for these three, 9,000. What about the greatest common factor? What was the only thing you were able to factor out here? 5. What was the only thing you were able to factor out here? So the only factor that goes into 360 out of these two is a 5, and it's the only thing that comes out of this one right here is a 5. So the greatest common factor that goes out of each one of these three is only a 5. Then panic happens. We like a little bit of panic. It means leverage. Those powers. Same deal. The best part about this question, though, is you don't try to plug it in because it won't fit in your calculator. Okay? We want the answer written with exponent. Just need to make your slide a little bit bigger. So I'm going to write this one first. 5 to the 21st times 7 to the 10th times 13 to the second. And over here is 5 to the 15th times 7 to the 12th times an 11. And one of the best things about this question, it's really only one step. Okay? Let's think back to a special moment in your math education when you had to factor polynomials. And you had to factor out the greatest common factor. So we're going to factor out the greatest common factor out of these two terms. So that means we want to make it a multiplication problem. We want to take something out that is common to these two terms. So you first look at the x's. That's an x to the third. That's an x to the fifth. What's the most x's each one has in common? How many? I can take 3 x's out of this, x to the third out of this one. Is there an x to the third I can take out of that? Is there an x to the third with 5x to the fifth? Is there not? Yeah. If this is x to the third, that's the most x's I can take out of this term. The most x's I can take out of this term is an x to the third. Does that have at least an x to the third to give up? Yes, it does. So then that's 5. So I'm going to factor out an x to the third. So no, it's reversing distribution. We factor out that x to the third. When I factor something out, since I'm reversing distribution, distribution means you're going to multiply it in. So when you factor it out, you're dividing the x to the third out. So when that x to the third divides out, in the first term, no more x's. In the second term, x to the fifth divided by x to the third, how about this? X to the fifth divided by x to the third is going to leave an x to the second. You subtract the exponents. Then we move on to the y's. In this term, the most y's that this term has to give up is the y to the first. Is there at least a y to the first over there? We have y to the fourth. Does it have at least one y to the first? Yes. Yep. So I can factor out a y to the first. So I'm going to factor out a y to the first. So y to the first factored out. So I'm dividing each one by y to the first. Here, the y reduces completely. So my first term has no y's in it. Over here, y to the fourth divided by y to the first, we subtract 4 minus 1, I'm left with y to the third. This is 2. And this is going to have y to the third left over. And then you go to the next one. The next factor is z. This one, I can take z to the fifth out. But is there enough z's over here to take a z to the fifth out? No, it doesn't have enough. The most z's we can take out is a z squared. Can we cover a z squared here? Yeah. So the most z's we can take out is a z to the second. So factor a z to the second out of each one. So there's a z second factored out. So divide by z to the second. Z to the fifth divided by z to the second. 5 minus 2 leaves z to the third. So there's a z to the third here. Over here, the z is reduced completely. That's what we're left with. That's factoring. Factor out the greatest common factor. And we know it's right if I multiply this back together and I get the original question. But now we're still dealing with numbers. One at a time. We look at the fives. We have a 5 to the 15 and a 5 to the 23. What's the most fives those two have in common? 15. The most, if they were going out to lunch, they were two friends going out to lunch. One has 5 to the 21, 21 fives in his pocket, and the other one has only 15 fives in his pocket. And they were going to split the bill even. 5 to the 5, so 15 fives and 21 fives. If they're going to split the bill evenly, the most that this person can spend is the most that this person has. They can only spend 5 to the 15, and this one can only spend 5 to the 15 if they're going to pay even amounts. That's the most they have in common. That's the greatest common factor. What's the most five that each one has in common, that each one has? So I'm going to be able to factor out a 5 to the 15. I'm going to write this down over here. Maintain my color schemes. Then we go to the next factor, 7 to the 12th, and this one has a 7 to the 10th. So they both have a factor of 7. But what's the most number of sevens each one has? 10. They each have 7 to the 10th. So I'm able to factor out a 7 to the 10th. So I can take 5 to the 15th out of each and a 7 to the 10th out of each. 10 and 12, the most they have in common is a 10, 7 to the 10th. And then the next factor is an 11. Do they have 11 in common? No, so you can't take it out. It's not a common factor. And then over here, there's an extra 13 to the second. Is there a 13 in common? You can't take a 13 out. We can only take out common factors. So that's the greatest common factor that you could possibly take out. So when I said, this is the good news, that's the most you'll be able to take out completely. You don't have to do another step out of this. We're going to be at the answer. But we just have to do the division. So when we factor, it's going to look like this. I'm going to divide out a 5 to the 15th, a 7 to the 10th. Divide by 5 to the 15th times a 7 to the 10th. So here, 5 to the 15th reduces completely. What is 7 to the 12th divided by 7 to the 10th? Look at 7 to the second. So that's 7 squared. So 7 squared times 11. Over here, 5 to the 21st divided by 5 to the 15th. So I'm going to be left with 5 to the 6th. So 5 to the 6th times 7 to the 10th divided by 7 to the 10th reduces complete. That's a 1. And then 13 squared does not reduce at all. 13 squared. So my least common multiple is this. Now I'm going to write it out. It's a 5 to the 15th times a 7 to the 10th times this 7 to the 2nd times an 11 times a 5 to the 6th times a 13 to the 2nd. I have to clean that up, but you would not leave it like that. So first thing, start with the smallest factor. So out of those numbers, what's the smallest number? Out of all those bases, what's the smallest base? There's not the power, just the base. 5. So you have a 5, a 7, 11, 5, and a 13. So the smallest base is a 5. So I'm going to multiply, and I'm going to take an extra step here. I have a 5 to the 15th and a 5 to the 6th. So we're going to multiply those two together. The next biggest base is 7. So times 7 to the 10th times 7 to the 2nd. That's those two. And then the next biggest number is an 11 times a 13 to the 2nd. And then try not to be over anxious because it's very easy to get this one a little messed up. 5 to the 15th times 5 to the 6th is 5 to the when you multiply, you add the exponents. Times 7, 10 plus 2 is 12. And then times an 11 times a 13 squared. That would be the first number they all go into even. And you would not multiply that out, you would just leave it as is, because it would not even come out in the color. And the greatest common factor is just this column right here, and that is just 5 to the 15 times 7 to the 10. That's the biggest thing you can take out of both numbers. So when you see a problem written like that as x of powers, you're just taking up common powers as your common factor. Same rules apply. In 8.6, we're going to answer this question. Is 0.9 repeating the same as 1? Is it exactly equal to 1? 0.9 and 99999, whatever, equal to 1, exactly. Well, we're going to see if it is or not. So 8.6, we're dealing with fractions that repeat or don't repeat, and fractions that terminate or don't terminate. In other words, in 8.6, we're going to be dealing with rational numbers and irrational numbers. Well, first thing I asked you over there is question number 8. Write these as exact decimal. So what is the exact decimal value of 304? Yeah, I always like to leave it at 0, so 0.75. Because I want to make sure everybody understands that's a decimal point and then my 75. That's a terminating decimal. It has a last digit. It terminates. When I convert number 9, the first thing you want to make sure you do is don't forget to put a negative. And then the next thing, how are we actually converting these things? What operation are we doing to make sure we get a decimal value? How does it work? How are we going from fraction to decimal? Because all we know is parentheses, exponents, multiply, divide, in order to flip, right? Add, subtract, left. So what's going on? How's it converting? What operation? Division. Right here, this was how many times can 4 go into 3 even? Well, 4 can't go into 3 even, so in the ones place, 4 goes into 3 0 times. So it goes in 0 times, so we'll put in a decimal. Put in a decimal. And we add a 0 in the tens place. So now in the tens place, we're looking at 30. 4 goes into 30 7 times. 7 times 4 from the tens place looks like a 28. So when you subtract, there's a decimal there. And when you subtract, you get a borrow. So that's a 2, that's a 10, and we get a 2. 4 can't go into 2 in the tenth place, so we have to add a 0, and now we're in the hundreds place. Treat it like a 20, 4 goes into 25 times. That is now a 0.20, and now when you subtract, it goes in evenly. That's how this 0.75 happens. It's division. Same thing here. I've already got the negative, so when I do the division here, this is how many times can 5 go into 6 evenly? Well, because 5 is smaller than 6. In the ones place, 5 goes into 6 one time. So we get a 5, and then we subtract, and then we subtract, and we get 1. So in the ones place, we're left with a 1. If we did anything, we'd have a remainder. 1 and 1/5 left over. If we wrote a mixed number. Well, we want a decimal. So now 5 can't go into the ones place anymore. So now we got to go to the tens place. So we put a 0 there. Now we're treating that 1.0 as a 10. From the tens place perspective, we treat it like a 10. 5 goes into 10 2 times. That is exactly a 10 from the tens place. When we subtract, it reduces completely. So that is 1.2. Since it was a negative, it's a negative 1.2. Now, There's a nice little trick instead of doing division on number 10, 50 into 47. Decimal places are based on what power? Decimal. Powers of who? You hit tens, hundreds, thousands, 10,000s, powers of what? Tens, powers of tens. If I gave you this fraction, 9 over 10, what would that look like as a decimal? You have the 9. There's my decimal place. If I divide by 10, what happens to the decimal? Anytime we divide by 10, we're just moving the decimal. So I'm going to move the decimal how many times from which way? What? Left, how many times? Once. This is 0.9. 9 tenths, 90 cents. If I have 9 over 100, so that would be a 9, and there's 2 zeros, so I'm going to move it twice. There's my decimal. I have an empty loop right there, so you fill it with a 0. So I have 0.09. 9 hundredths would be 9 pennies, 9 cents. So 0.09, I have a 9 in the hundredths place. 9 hundredths would be a 9 in the hundredths place. So this right here, what's nice about this 50, if I multiply by 2 over 2, I can change 50 into 100. Because if I can get 100 down there, I'm just going to move the decimal 2 times. 2 times 47, that's a 94. So this 47 over 50 is exactly the same as 94 out of 100. So if it's 94 out of 100, you take the 94, move the decimal 2 times to the left, 0.94. Again, another terminating decimal. So far, all of these terminating decimals can be written as fractions. Fractions can be written as terminating decimals. Terminating decimals can be written as fractions. Then along comes 5 over 9. That means 9 divided into the 5. So in the ones place, 9 can't go into 5. So in the ones place, it goes in 0 times. So then we have to add a decimal, treat it like a 50. So in the tenths place, 9 can go into 50 5 times. 5 times 9 is 25. And then you subtract. 50 minus 45 gives me 5, 0.5. 9 can't go into 5, so we got to add a 0 in the 100 place. Treat it like a 50. So from the 100 place, 9 can go into that 50 5 times. So I get in the 100 place of 45. And then we subtract. So 0 minus 5, we're going to borrow. That's a 5. We have 0.05. So in the 100 place, 9 can't go into that 5. So we got to add a 0 and move on to the thousands place and treat it like a 50. 9 can go into that 50 5 more times. And then you start to see, well, there's a pattern happening here. Because every time I do this, 25, I'm going to get the same remainder. And I'm going to keep multiplying by 5 forever. And we call that a repeating decimal, because we get a pattern that keeps repeating. But that repeating decimal can be written as a fraction. So how do you write it as an exact value? Well, you can't unless you put a bar over it. If you don't put a bar over it, then you don't have the exact value for 9/5. Because if all you do is go, this is 0.55, and then you don't put a bar, well, that's 55 hundredths, which is going to be 11 over 20. That's not 5/9. You don't put a bar over. Can you just write 0.5 and then just one of those sides? Yeah. Because now you've indicated the 5 repeats. 5 per day. Rational numbers. Rational numbers are any number that can be written as a fraction. And they include terminating, or repeating decimals. So that means all the whole numbers, all the counting numbers, all the integers, and then all the fractions, terminating and repeating decimals, they're all rational. And the ones that are not rational are irrational. So these can be written as fractions. Irrational numbers cannot be written as fractions. Their decimals do not repeat, do not terminate. Their decimals will not repeat or terminate. There's no last digit and never repeats a pattern. One of the most famous irrational numbers of all time is the number pi. Pi is approximately 3.14. If you write it like that, that is not the exact value of pi, it's just an approximation. No one can write out all the digits of pi because it never ends. It never repeats a pattern. You can't put a bar over anything. So when you write something like this, you could write 3.14159. You can go dot, 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 and that would be, hey, this goes on forever, but nothing repeats, nothing terminates. You're not writing an exact value. You're just showing that it goes on, keep on going. Another classic irrational number is the number e, which is 2.71828. And again, it goes on forever. That's the number involved with logarithms, the base of a natural logarithm. You also have the golden ratio, but all the square roots, all the radicals. If you don't have a nice, perfect square root, the square root of 2, that's not a fraction. That is going to be approximately 1.14, no, 1.414, but it goes on forever, no last digit. The square root of 3, 1.732, no last digit. But square root of 4, square root of 4 is exactly 2, and that is exactly 2 over 1. I can change it into a fraction. So some square roots, rational. Other square roots that are not perfect squares, irrational. That actually talks not only that. Let's see. Talked about that, terminating and repeating that. We didn't talk about that. Okay. Convert these decimals into fractions. Here comes the fun part. Bring it on. Here's how we convert into fractions. So we have 0.625. What place value is that 5? What place is that 5? None. Thousands. Tenths, hundreds, that's in the thousands. So since it's in the thousands, we know that the denominator is 1,000. What's in the numerator? 625. That is 625 thousandths. That's it. The directions even say, don't worry about simplifying. And here's why. We just want to make sure you know how to convert what place value and what to put in the numerator, what to put in the denominator. Make sure we make that connection. Don't change anything. We've been doing exactly what we need to do. Same rule applies right here, even though we have a 1 in front. 1.234. First, figure out what is in the denominator. What place value is the 4 in? Thousands again. So make sure you're counting the place value correctly. Tenths, hundredths, thousands. So you have 1,000 down below. And then the numerator is that number without the decimal. It is 1,234. Because if you took the 1,234, and there's the decimal, and you divide by 1,000, you would be moving the decimal 3 zeros 3 times to the left, and you would get 1.234. So the last digit tells you what place you're in. So it tells you what the denominator should be. And then you put the numerator as the number without a decimal. That third one down there, we have negative 0.1200008. Well, first thing, don't mess this up. Make sure you put your answer, it's going to be a negative. And then what place value is the 8 in? 100,000. 100,000. So the tenths, the hundreds, the thousands, the 10,000s, the 100,000s. So the denominator is going to be 100,000. What's in the numerator? Make. So 1 divided by 9. 1 divided by 9. Divided by 9. Got any predictions about 1 over 9,999? 0.30. Another one. And then this one would be 0.40. You think it's repeating? Oops, I thought that was it. Yep, they're repeating. This is repeating 1 digit, that's repeating 2 digits, 3 digits, 4 digits, 5 digits, 6. Habits. Okay. Is 0.9 repeating equal to 1? So I'm going to show you that yes, it is. And then I want to show you how to convert any repeating decimal, because repeating decimals can be written as fractions. Terminating decimals, those are simple. What's the last digit? How many decimal places? That's your denominator, what places it in, and then put the number without the decimal in the numerator. That's not bad. But how do we convert repeating decimals? It takes a little bit of work, a little bit of stepping. So the first thing we're going to do is take a look at this. And 1 divided by 9, 0.1. 2 divided by 9, 0.2. 3 divided by 9, 0.3. 4 divided by 9, 0.4. 5 divided by 9, 0.5. 6 divided by 9, 0.6666, repeating. 7 divided by 9 is going to be 0.777 repeats. 8 divided by 9 is going to equal 0.7 or 88888 repeating. And then 9 divided by 9 is going to be 0.999 repeating. Well, what's 9 divided by 9? It's 1. That's not true. That's just a nice winky one. Okay, it's not always triple. So we do this. Give my special place here real quick. I'm going to start with this. I'm going to let this variable, let n equal 0.9 repeat, or just going to write a few nines that I like to write up. 0.999 repeat. Okay? How many digits are repeating? Is it 2 nines repeating? Is it just 1 9 repeating? Is it 3 nines repeating? How many are repeating? Just one, just 9. So now I'm going to multiply both sides by 10. So here's what's going to happen. I need, 10 times n, 10 times n. So 10n is equal to, this decimal is going to move right there. And I get 9.999 repeat. So I start with what I got to figure out. I got to start with the 0.9 repeat. What the heck are you? I'm starting with 0.9 repeat. I'm going to let n equal that. Then I'm going to multiply by some power of 10 to move the decimal. And you'll see in the next example. So let me show you what I've got. I have n to start with. N is 0.999 repeat. And I have 10 times n equal to 9.999 repeat. That's what I created. Now I'm going to subtract. Subtract to get rid of, that's not great math, not technology, to get rid of the repeating decimal. So watch. I'm going to take my 10 times n, which is 9.999 repeating, and I'm going to subtract this one from it. I'm going to subtract 1n from this side, and I'm going to subtract this on the other side. Because it's equal. So I'm going to subtract it on the left side, I'm going to subtract it as an n, because they're like terms. And I'm going to subtract that from the number side, because they're like terms. Everybody okay? So when I do that subtraction, what's 10n minus 1n? With 9n. 9.9 repeating minus the 0.9 repeating. So the 0.9 repeating is gone. It's 0. All I have left is 9. All the decimal is gone. So now I have 9 times n equals 9, divide by 9. And I end up with n equal to 1. Well, wait a second. N started off as 0.9 repeating. I just got n equals 1. So that means this one is the same as 0.999 repeating. They are the same thing. One is exactly the same as 0.9, but it's 0.9 repeating forever, an infinite number of nines repeating. An infinite number of them. So how do we know? Get to infinity and tell me what to get. We get one. Okay. What happens if it's more than just a 10? So I got 2 minutes. I'm gonna get this one. Right here. 0.98 and then 1, 2, 3 is repeated. So the first thing is you're going to start with your n is equal to 0.98123 repeat. And what you have to do is you have to get rid of the 0.93 repeating. So what you need are two terms where the decimal is the 0.123. So here's the problem. To get to here, so I just have this much, I have to multiply by 100. 100 times each side. I got 100n equal to 98.123 repeat. I suddenly give you the regulation to it. Give me a second. But if I only use this with n equal to 0.98123, I can't get rid of the decimal because the 98's on that same side. So I need more than just this. Remember, there's another 1, 2, 3 over. I'm going to actually have to move the decimal here now. Or actually, let's do it with this. I'm going to have to multiply by another 1,000. Because I got to now move it 1, 2, 3 times here. So that's going to give me and that is going to equal 98,123.123 repeat. So I have I have 100,000 n equal to 98,123.123 repeating. There we go. And I have 100 n equal to 98.123 repeating. So now when I subtract the repeating decimal is going to cancel out. On this side, 100,000 minus 100 is going to give me 99,800 or 900. You're going to borrow, that's going to be a 10, that's a 9, that's a 9, so 99,900 n. And over here, that reduces on. Then a borrow, that's a 1, 13, you get a 5. Then a borrow, that's a 0, that's an 11, and then we have 2. And then I have a 0, and I have 98,025. And I divide both sides by 99,900. And so this right here is equal to 98,025 over 99,900 as a fraction. And I can check my answer if I just calculate it. 865 by means 0.98, 123. Appreciate your patience with me. This is not homework. This is just for you to kind of orient your study, what to focus on. There are just a summary on the front and practice problems on the back. And again, that's what we're doing on Tuesday. So you're ready for Thursday. Have a good weekend. Don't forget to do your quiz.